Everyone's here. We have Kyle Ray. Thanks, Kyle, for joining us, and looking forward to this.
Yeah, great. Thanks for inviting me out. It's been a really fun weekend, plus a bit more. So, yeah, my name is Kyle. I guess everybody probably knows me at this point.
Hi, Kyle.
So I guess I'm quite a literal-minded person, and so when I think about the physics of intelligence, I'm really stuck on the physics part of it, you know, and that's typically my mode of working is through examples, through like trying to simulate and look at the way that information theoretic and stochastic thermodynamic principles, how they emerge, what mechanisms will they emerge in specific examples. So when I think about intelligence, somebody who studies thermodynamics and stochastic thermo, I think it's not a big surprise that the first thing that I think about is Maxwell's demon. Maxwell, in this case, Maxwell is the demon. I always like to find a new picture every time I talk about Maxwell's demon, because there's like so many. For a while I was like, you know, of course you're on like, let's make the AI naked, but that's tacky now, so I won't do it.
Did he say that? Intelligence?
This is a word-for-word transcription of exactly what he said.
Really?
No, this is my paraphrase.
Okay.
So,
paraphrasing than his.
yeah, this is a lot of paraphrasing. So, you know, the fellow Maxwell's demonologist, Alec, a few days ago, it kind of explained the basics of Maxwell's demons. I'm not going to go into a lot of detail about it, but the fundamental idea is that you have some intelligence inside of a box of kind of thermally equilibrated or steady state particles, and that little creature is able to observe and then like open a trap door and sort based off of this thing. So like all it does essentially is it opens the door if it likes one particle, and it will close it if it doesn't like that particle. And then what it can do is it can sort things, and if you can sort things, then you create some kind of pressure differential of some sort, whether it's temperature or density or whatever. And what that means is that you can then violate the second law if you just throw a demon into the system, right? And my paraphrasing here, the hope is that it's trying to talk about what I think Maxwell's point was, which is that you shouldn't be thinking about intelligence and thermodynamics at the same time, because it's like you're trying to put magic into something else. And so in some ways, I think the original point of this paradox was like to tell people to stay away from the physics of intelligence, which I think is kind of ironic. And kind of thinking about what Alex said the other day about us as demonologists, I think that sometimes we're more like exorcists of Maxwell's demon, right? In the line of like Szilard, who several decades later came and said, that's not really a tiny intelligent demon, that's an incredibly simple system. That's a switch where it's correlated to two things. It's correlated to some property of the particle that it's trying to observe, and it's correlated to some door. Yeah, and maybe it has some memory, that can help. Maybe switch in some ways is a memory, so you kind of like operationalize that thing. So this isn't intelligence, this is just a little, really simple machine, and if we build it, then there's no issue, right? The exact cost that it takes to operate that switch is exactly any kind of benefit you could get from sorting. So that's, you know, I think of Szilard as the exorcist of the Maxwell's demon. And I find this to be an incredibly important paper. And it really, for me, there's a lot of discourse after this over the century about this issue, but I feel like he just kind of already solved it. And it demystified the whole thing. So if you build this thing, we're good. If you actually come up with an explicit model, use physics, there's no paradox at all. And so in some ways this kind of like ended the intelligence and thermodynamics question for me. It was like, but then this happened, right? So what is it? You have this issue where like, well, that's just a correlated switch with some memory. Now we have these machines which are a bunch of correlated switches with a bunch of memory, and you can talk to them, and it's very confusing. And I don't know what to make of it, right? Maybe that's because I'm not an AI researcher. I'm more of like a person, like a normal person who uses ChatGPT to try to help themselves sometimes, and I'm always amazed by it, and I'm rarely helped by it, but I'm always amazed by it. But this kind of reintroduces. We're bringing Maxwell back. We're like, okay, is this incredibly simple system? Is this actually some like intelligent demon that maybe can break physics or at least break society? So,
At least. Is it
The latter seems more like.
yeah. Yeah, I don't think it's breaking physics, but society, I don't know. We have to at least cover our bases on that one. So yeah, I guess I'm going to punt a little bit on intelligence because I don't really know exactly what it means, and I do find it quite confusing. So one of the ways to try thinking about it is I start just like putting devices on an intelligence line. It doesn't have an axis because I don't know what intelligence means, but I think that the human brain is over here, and that things that are less intelligent are over here, just vaguely speaking. And there's something like an analog clock. I thought about this because I was spending time with my uncle, who's a philosopher, and we were trying to fix an old family clock like a month or two ago. And we had thought it was broken. The family's like, oh, this is a broken clock. But of course that wasn't really what was happening. It was just like you have to wind it and you have to look into it, you have to look back and it starts to do something, it's doing the wrong thing. But then you realize, oh, it's confused, right? That's how I kept talking about it. I'm like, oh, it's confused. It just thinks it's 6:30 and it's not 6:30. But of course my uncle was totally against that because he said, well, it can't think. And so we kind of got into a back and forth about it. Like, okay,
Did you get?
is it so different than our brain that's all organized in a certain way to say, I think it's this time? It's unclear. But something he did say, which is that even if you convince me with your logic and your physics right now that we're the same, I'm going to still say you've avoided what I mean by thinking and intelligence because I know kind of fundamentally that clock doesn't think it. And I think it's a valid point in that in some ways you might be able to prove that there's no difference in terms of like the makeups. It's just another automaton, just like we are. But I don't think it's intelligent. And this is my talk, so I'm putting it over there. And the same thing with the Solar engine, right? It's just this correlated switch. I can program it up on the computer, I can simulate it, and there's nothing mysterious going on there. And as we move up, we've got the Chinese room thought experiment, we've got chess bots. These things I put them in this order. Some people might think it's the other way around, but somehow I feel like convincing somebody else that you are able to just totally converse in Chinese is more intelligent than playing chess.
Wait, I thought the Chinese room is supposed to have the same behavior as a person.
Well, but same behavior, but I don't think it's intelligent.
But you're referring to like the architecture of the lookup table and the input and output, right?
I'm referring to vibes. This is a vibe chart. I really do mean this. And I think it's important to remember, like, fundamentally, most of us are operating on vibes here. Nobody has a perfect definition of intelligence. Nobody has a perfect definition of consciousness. We don't know.
But just to be clear, you're not defining intelligence based off behavior. It has to be what the internal thing is too. Because I feel like the Chinese room is usually about consciousness, not about intelligence.
Totally, right? I've just thrown a bunch of stuff up online, and I haven't defined anything. And I do want to be clear about that. I haven't defined anything. I'm just putting stuff on here. And I think somebody might argue the other way around. I don't know, because it's a big lookup table and that's it, that it's not intelligent. But I do bring the behavior in there somewhat, because you're saying it behaves just like a human. But I know it's not, so I'm going to put it less on the intelligence line. Okay, right, and then we have large language models, which I've also put here less than intelligent than a human, which of course is debatable because it obviously can do lots and lots and lots of stuff that it couldn't do much faster. But again, it's looking stuff up. I don't know. Skynet, obviously, it's more intelligent than human. So, because it doesn't exist, so somebody made it up to be that way. Now, one of the interesting things that I noticed when I started putting things down and why I kind of stopped this process at this point was I got confused now because I want to talk about the physics of intelligence, but like a chess robot, like a large language model, and presumably Skynet, they all run on the same hardware. So do they have the same physics? Because when I think about physics, I think about hardware. And it's a more complicated question than that, right? Because these are different softwares running on the same hardware, displaying different behaviors, and you get to this kind of like hardware versus software question.
Yeah, I mean, one thing I missed, nothing on that is biological except you didn't list.
Yeah, dog.
I don't want to make anybody mad. But
You don't want to call it.
unfortunately, dogs would be way farther to the left than most people might agree with.
More
in
or
my
less.
personal-
Where would you
More or
put
less
it?
than Norqual.
Yeah, where would you put a dog?
I admitted it on purpose. So
Yeah, what happened to vibes here?
But I think that's interesting
He's
that like
allergic.
your
Oh.
spectrum is completely computer architecture, like the computer hardware and like biological hardware. It didn't come into that scale anymore. Like, in the way that you just presented it. I'm not saying that you
well,
believe this.
no, it's probably because I don't think about biological hardware. I think about hard hardware, right? You know, and that's what I spend a lot of my time thinking about, which is what I'm about to talk about, is like digital computing. And it's something that I can wrap my head around and understand, and it is very true that what we run our language models on today, the physics of those, is a combination of the learning algorithm and the computer, the actual physical computer. That's like the physics, you know? So if we sit down on our computer and run ChatGPT today, not potentially in the future, but right now. And so I'm totally gonna punt on intelligence and software, and I just wanna talk a little bit about the hardware as it is today. And what I mean by that is kind of like, what's the physics of digital logic? So in a pretty generic kind of setup, we can think about digital logic as some particles that exist in some phase space. So you have a system, these orange and blue dots are meant to represent just realizations of the system. They evolve dynamically in continuous time and in continuous space. And this blue line represents the forces on the system, right? And you can really think about a lot of systems like this. And the existence of like a 0 and a 1 state essentially is the coexistence of two different regions of space that are distinguishable, meaning that they can, if you're here first at time t, you expect it to be here for some long amount of time in that general area. And an erasure gate, for example, which I'm trying to illustrate here, would be to somehow deform this potential, do something to this physical system over time so that at the end, they're all over here. And I'm starting to say zeros and ones and erasures, and that's because we always think about this stuff actually in terms of a coarse grain, right? So zeros is basically every single piece of microstate space that's over here, and essentially every single piece of microstate space that's over here, we call it one, and it's good to distinguish those because there's a huge separation of time scales, right? Mixing between zeros is very fast, mixing between zeros and ones is incredibly slow, especially if this barrier is very high compared to the thermal agitation. So this is kind of a standard picture of the way that people think about digital logic, and we know how to do these things efficiently. So it turns out that you can actually do this operation without spending some work. It's going to take KT log 2 to work to do this thing, which has been for a super long time, and we basically do know how to design computers that do that, right? So there's some work that was being done in Jim's group when I first started working there, and the basic idea here was that they'd use some superconducting circuits in order to perform an erasure, and we can see in real time what that might look like here. So you have this green, this is the instantaneous distribution, and blue is the control. And what you'll notice is as you move that control, the instantaneous distribution is always like reacting to it. It's always some type of conjugate distribution at all points in time as you go, right? You lower the barrier, you tilt it over to one side, you raise the barrier again. And while it's not equilibrium, right, it is locally equilibrium, kind of according to being close to one of these wells. And if you do an erasure like this, it does take just about KT log 2 energy. Yeah, it was shown experimentally in different settings. This one I really like. And the underlying efficiency here comes from being quasi-static. It comes from that idea is every time you change the drive, the system is allowed to relax. It's let it locally equilibrate to the drive. But it is a bit problematic if you want to compute in finite time, right? Because quasi-static theoretically would take infinite time, but then there's a problem because in infinite time things start jumping back over, right? So effectively a long time, let's say. If you take this exact protocol and you start speeding it up, it's gonna destroy it. It's gonna go very poorly. And what I mean by that is that you're gonna end up wasting a bunch of energy. So that can be seen with just a really simple example. Here, instead of doing any erasure, I'm just gonna take this bit, which is the equilibrium distribution near the bottom, and I'm gonna move it over here. And I'm gonna do it slow, I'm gonna do it medium, and I'm gonna do it fast. right? And what you will observe is that in the top situation, there's not really any signature that you're moving, right? This is the indicative of it's always responding to control, it's bouncing around at the bottom, it's gonna cost 1 land hour. Of course, the minimum of this, if we took it into time, is 0 because we're not actually doing anything, we're just translating. But in this case, I got a pretty good benefit here going from infinite time to just a really quick simulation on my computer, and it only cost, less than KT energy. Now I can speed it up, shave off 5T or whatever, arbitrary units, and then I get something like this. You'll see there's a little signature, but we're still okay. This is kind of a linear response regime, yeah.
Sorry, is L a Landau?
L is a land hour, it's KT log 2, yeah. Just kind of like what Gavin was saying, that you can think that the KT scale energy is kind of like a relevant energy of computation. You always have to scale it to the thermal energy. In this case, using KT log 2 because it's erasure, and conventional computing is based off of erasure, so it's a pretty big deal. So, and it is kind of it's the most expensive binary gate, so it's kind of like a conservative guess for this scale. Now, if we speed it up again by the same factor, it's pretty obvious that the situation is very different. So it's no longer reacting quickly or any kind of linear response. These things shoot way up the side, right, of this thing. You're giving it a bunch of potential energy, and then when it lands, fortunately this guy's over it. Anyways, when it lands, they have to ring down, they have to spend all their energy, and it's like, okay, I'm faster, but I spend a bunch of energy. And this is kind of like a good way of seeing how this energy delay barrier, as they often call it, where it comes from. That there's kind of these two regimes, right? The work cost scales as 1 over tau, and there's an efficient regime over here. There's some minimum work for the process, and in infinite time you get over there, and you can be pretty efficient if you're over here. But the second you want to drive this thing really fast, you go into a different regime, the fast regime, which unfortunately is how we want to run our computers. So we can think about this as kind of one of the major reasons that a computer today doesn't take on KT scale energy, right? This is a tiny slice. This is very generous actually. So it's imperceptible if I was actually telling you how small KT log 2 was compared to actually how much energy a computer takes. And then there's the implementation cost, which is all this other stuff.
Like how slow is, because maybe what if you just run stuff in parallel? Like if we have a lot of things that we care about running in parallel, it's maybe okay if each operation isn't extremely fast.
Yeah, and in fact, this can save you a lot of energy.
Yeah.
I'm trying to think of that these electrical engineer at Berkeley, Eli Yavlanovich, and he kind of very nicely makes this case, and I think tried to make this case to Intel specifically, that in fact they could save a lot of energy by only spending a little more time, and they kind of told him, get stuff, we have to go really fast, I would say.
There's also at least one paper, but I can't remember the name. I'll try to find it for you. That does say, just make things parallel, and then there's the trade-off between what you can parallelize and.
Yeah, I guess there's some fundamentally serial operations that you can't parallelize.
Right.
Yeah, and you have to assume people claim the brain is way more energy efficient than computer, which I'm not going to talk about. But if that's the case, it's by massively parallelizing and being slow, right? So.
And then one more thing too.
Yeah.
I mean, we spend a lot of our time thinking about this problem, and the way we have counter-diabatic forcing, and we change the shape of the barrier, we stiffen it when we move it, and so if you have other degrees of freedom, you can knock your energy costs down, and you can even calculate the best way to do it and all that stuff. I don't know if that's where you're going with this.
Okay, so yes, but also, unfortunately, physics doesn't always give you total control of the potential energy surface. And so, while I love adiabatic and counter-adiabatic stuff, and the math is really nice, it doesn't mean that you can actually design protocols like that, given a working circuit of any sort, with very limited control.
We should talk later, but if given that restriction, the thing I would have, if this were Telluride, what I would have presented is, here's the optimal way to do it. Involves the loss or steam distance and Fisher information, all this stuff, for coming up with the right, the best thing you can do given your protocol nods.
Yeah, but I would have said, that's great, and I love this because I love stochastic thermo, but I also want to see a physically instantiated logic device that permits all of that control.
Yeah, let's talk.
Yeah.
I should find out more about, we should make more contact with real devices.
Yeah.
which Jim and colleagues have been doing.
Okay, so yeah, we get the energy delay barrier. There's also this fidelity trade-off, right? I think this is starting to feel very familiar to Gavin's talk, right? And this is, here's a kind of cost that, like, Alec and Chris Roshinsky and Jim, you guys worked on this Ubatic kind of protocol stuff. And yeah, you find this kind of scaling. Like, it pops up all over the place. Nobody is surprised to say, yeah, there's a 1 over tau cost scaling for speed, and there's a fidelity trade-off that's like the log of 1 over epsilon or something like that, or it scales. And basically, I would say that the intuition here is that increasing determinism, that's increasing your fidelity, means a higher energy scale, which stops particles from bouncing around from thermal agitation, and that basically increases your cost of control, because when things go out of equilibrium, they kind of perturb up higher, and then they have to dissipate more energy, maybe, roughly speaking, right? So we have this 3-way trade-off of work, fidelity, and speed, basically what Gavin said. I'll just put it up there, and you observe this all over the place if you kind of work out optimal control stuff. One interesting thing that we've found over the last few years, where within Jim's group, is that this doesn't always happen kind of in all regimes. So what I want to talk about here is kind of the background part, where I introduce to you my perspective before I start speculating wildly about AI, is how we've tried to get around, in some ways, circumvent that 3-way trade-off in practical systems that are like physically viable systems with controls that experimentalists tell us, yes, we can do that. So it comes down to this idea. What's in this well? What does this really mean? And there's 2 very different perspectives, almost opposite perspectives. If you're a stochastic, thermo, or digital logic expert, you may look at this and say, that's an erasure of information. You can't, basically this is associated with its conjugate distribution, like I was saying, right? A Gaussian lump at the bottom. But if you're into dynamics or freshman year physics, you look at this and you say, this is a spring. This thing will oscillate a particle back and forth. If you put a particle here, it's going to bounce back and forth. Or in phase space, it'll rotate. And both things are true, and it depends on the physics of what's going on, right? There's different kind of dynamical regimes of how something might evolve according to just a harmonic potential. And that's kind of what I'm showing here, is there's these different dynamics that you can take advantage of. So on this axis, we have damping or kind of coupling to your thermal environment. On this, we have how far away you are from the steady state to start. And what you'll see is that if you start far from the steady state and your damping and coupling is quite low, then you get, of course, these rotations. It's a noisy rotation because there's still thermal agitation. But this thing kind of slowly spirals towards the center. It's not just an existence of particles at the center. This red line, of course, the red circle, of course, represents basically what you'd expect from the thermal distribution. Okay. And you can even see if you start close to the steady state and you have low damping, there's still some kind of signature that's maintained, right? There's a part of this that is empty. So that's kind of hard to use, right? Because this thing is stochastic, it needs to be very clearly kind of outside of this region to be useful. But we have shown with this idea of momentum computing, kind of coupling, using the same kind of circuit that we use to do the erasure, that it's viable to do a fast computation, meaning that you're operating not on the time scale, the kind of time scale that the things dissipate down to the bottom, thermalization, but you operate on the time scale of the plasma frequency, the time scale that this thing goes from one side to the other. And yeah, you're going to lose some energy, but you're also going to recover a lot. So we can see this is a bit more complicated because this is a real system, so we have extra dimensions that are necessary to be able to control. And you'll see that, right? So this is a position space, this is just momentum, and these are just position momentum in each kind of dimension. And one thing you'll see is initially the information is stored here in position. Once we start the process, the information is going to get kind of muddy here in position, but it's going to temporarily go to being stored in momentum. And if you look at this phi dot plot, what you'll see is that those two initially on top of each other, because they're thermalized ensembles, separate out for the computation, and then they'll come back together at the end. When they come back together, that means that the information is now stored back in the position. So you're going back and forth between where you're storing your information. And maybe that's the insight here, is that it doesn't always have to be stored in position. And in fact, if you're trying to move things around in a non-equilibrium way, maybe it's better to store momentum during that point. Okay. And yeah, so one of the things we did is that's just kind of an example illustration, but we optimized over a bunch of different fabrication parameters and showed that in all these different byte dots, you could in fact find a place where you could do this kind of bit flip computation at less than 1 land hour cost.
But, what is your physical implementation?
What is the physical implementation?
Right.
This is a superconducting circuit.
Because we've got CMOS, we don't have momentum.
Yeah. So there is. It's a good point. But there are underdamped room temperature circuits as well.
Yeah, but yes, but once you go down to chip scale, basically the inductance is irrelevant. So.
Yeah. So I mean, it's a totally valid point. So
I'm just
yeah.
like, how can we use this guy?
Yeah. So this is kind of one of the things, like, we know that we can do this with the right dynamics, and the question is, how do we do it? It can be done here, and in fact, this is a really cool thing. I found this out recently. There are types of Josephson junctions that can turn on and off, and so the real gem here is to be able to do both, right? Because one of the downsides is if you're in this non-dissipative regime, you have to wait for it to ring down, and that can take a while. So what you really want is a resistance switch that effectively modulates the thermal damping, where you go low noise, you swap it over, and then you go high noise. That's actually viable with the right kind of cryotron device that's essentially just right there next to the critical temperature. And what happens is you just pump above it, and then it's very quick. It's picoseconds, quicker than picoseconds. Low picoseconds. And what it does is it...
Quick calculation.
Yeah, my enthusiasm.
We just watched the calculation of it.
Yeah, it was amazing.
Basically,
One
it's
of
like
those floating point operations.
You switch dynamic.
It switches dynamics. It's an extra path for the electrons, and they no longer go through the dielectric and the Josephson junction. They'll go through this guy, and it dissipates all the energy almost instantaneously. So that's very cool. But yeah, so.
I guess there's an idea that you need to be able to compute at different scales in order to do different operations. Like you want fast weights and slow weights and things like those. And then you want to do something at slow weights and then upload it to fast weights. To what extent does this go into that? Like you can compute in momentum, that's sort of fast computations, then you want to store it in some more durable memory.
Yes. Yeah, right. There's that duality where, like, this momentum is cool, but like I don't have any illusions that we're going to be able to have a complete momentum computer that's just only using momentum, because it's not good for storage, right? It's quite volatile, and so you're right. It's like switching back between these things. The position is very good for slow time scales,
Right.
but the momentum is quite good for fast time scales. Yeah.
And to some extent, maybe our brain does something like this. Like we are doing fast processing, like there's a system 1, system 2 clarity and things like that.
Yeah, like this might model really well tasks. Yeah, and I think that this is a big point of interest for me, is having the physics that underlies the computation match the algorithm that we're doing, and that way, it's kind of the analog computation picture, but with digital logic.
Yeah, I'm wondering. I think not unique to your work here, but oftentimes we play this game in non-equilibrium thermo, where we do the calculation of work, and it's like, in principle, this work is recoverable because like the potential is going down while the thing's over here. But like in actuality, we never usually say how you would recover that work. Do you have an actual mechanism where you're saying like the Josephson junction actually requires that small amount of work?
Like how it can actually get the energy back, you're thinking?
Yeah.
Yeah.
Is that already
So just to
taken care of?
I can tell you I have an idea.
Okay.
So ultimately, these things are driven by currents. Okay, and I'll talk about that in a second. Right. What I'm showing you, all these phase plots, those aren't currents. Those are phase differences across the Josephson junction. But when you drive it, you have to convert everything into kind of a current space in order for electrical engineers to understand what you're doing. And because it's currents, then I can kind of imagine that what you're using is you're charging and discharging a capacitor.
Okay.
Right. So you
That sounds
discharge a
very
capacitor
possible.
to drive it. And one of the cool things about these protocols, which I didn't mention, is they are time symmetric, right? So they don't violate the time symmetry of control. And so there's a lot of strength to being able to do stuff this way, at least in principle. And if we can do it, then all of a sudden, we're potentially like 10,000 times cheaper if we can somehow make a computer that this is now the dominant cost. Right.
Just so I understand, you mean if you have a situation where it's not just under damage, but you're not losing, it's gonna cycle around forever if you.
No, it doesn't have to cycle around forever. Because this isn't cycling around forever, right? This is one of those things like you have people who are like, I only want to do reversible computing, and people are like, I only want to do reversible computing.
Right.
No, we don't want to throw the baby out with the bathwater here. Like dissipation is useful.
Okay.
So we're
you're
moving it around and then we're dissipating.
So this is
right?
an
We're it's like
intermediate regime.
right. It's like billiards. It sounds really cool, billiard computing, but then it's like super unstable because there's no stabilizing force. Here, we're reintroducing a stabilizer.
Yes. Oh, you.
Yes.
Well, no.
Also,
Good question.
We need to pay some cost.
Yeah.
Then we need to lock in the calculation.
Yeah.
Right. And go on to the next.
Yes.
step. It's just not clear.
Yeah.
It doesn't mean you can't do a bunch of calculations in the middle and then lock in.
Yeah.
So mostly because we're going to see more something about these single calculations right now, then you don't have the choice. But yeah, if I can do a bunch of stuff and then dissipate and lock in, then
There's a certain setting where you can do that.
Okay. How am I doing on time? I've totally lost track.
You're at 30 minutes.
That's pretty
So
good.
you,
That's
I
great.
mean, if another 20 minutes is good for you, something around that order.
So just a little, we'll make it one moment work. So another thing I want to point out is that I talked about that three-way trade-off of fidelity and work cost, and there was another thing, computation time. And what you see in this kind of protocol, because essentially what you're doing is you're matching different oscillations, right? You have this plasma frequency, this particle going this way. Of course it's a distribution, but it's far enough separated that it's very unlikely that you're not going to be able to catch it in the right place. So what you'll see here is this blue is the work cost. You can see the horizontal is the computation time. So this is saying, it's not, I'm simulating this, so it's not hard to say, what if I stop it here? What if I stop it here? What happens? And what you'll see is that there are two minimums of work, which makes sense, right? There's the first oscillation over there, then it goes back, and then there's another oscillation over there. But there's these other oscillations going on too, and one of the things that you'll see is that the kinetic energy being minimum, which is what you would expect, would be the most important thing, right? You have this thing slide from one side to the other, it stops, and then you catch it, right? You want to catch it with minimum kinetic energy, that's the whole point. This minimum is corresponding to a maximum, right? And that can be explained by this third thing, which is, this is basically the velocity of the extra dimension that we need in order to control this system, and you can see that it has to be in the right phase, right? If we're in the wrong phase, then you don't have the right kind of symmetry with the initial and the final thing, and this thing breaks down, you actually cost more work, yeah? So there is these really interesting kind of non-monotonic stuff that appear, at least in these simple cases. Okay. And actually something that is also cool that Alec and I worked on is that it's actually true that when we were working on basically a precision bound for time symmetric computation, you might say, we found a way to kind of diagnose, given that a system obeyed a particular fluctuation theorem with time symmetry enforced, if it was able to support kind of the most accurate control allowable given the distribution. And what we found is that quasi-static type protocols, we ended up hitting this kind of effective bound where it wouldn't go below that. We weren't, down was more precise in this case. We weren't ever able to get down to the actual, what we think is the most physically realizable thing. But then when we introduced a momentum type protocol, we were able to control down here, close to what the kind of precision bound for dissipation would be.
What's that last line?
The black one?
Yeah.
That is physically unrealizable. So that was a loose bound that came before the
Oh, okay.
which is a really cool iteration, yeah.
I just want to comment since we didn't say it explicitly. This is basically generalized thermodynamic uncertainty relations.
That's the method that we used to figure out if we were meeting these bounds was, instead of basing just on the first moment, we looked at all moments of the entropy reduction. And so we were looking at the full distribution of entropy reduction and seeing if that could support the precise control. And just to point out, this used to be in my future work slide, but unfortunately, well, maybe fortunately, somebody out of Chilberto's group recently basically put out a paper doing this, but this doesn't just help with reversible computing. You can also use this type of thing for irreversible computing, and it's not a huge surprise. So here's this like simulation that I really like that I've been playing for a long time, but I'm gonna have to just start using plots from their paper probably. But so the idea, right, is you start separate. You put kind of like two little intermediate wells there, and then when they get close to the middle, you find some kind of optimal time to drop them into the middle. And then they
I
collapse.
also was literally planning to do exactly that
Yeah.
experiment. So okay, so we don't have to do that.
Well, no, they do have we will do it because they're using the
Yes.
optical well, which which I feel like there's lots of loopholes. So, but yeah, it's really good. It's good work.
Oh, I just wanted to point out Steve Whitman, part of the Chandler grouping, and is at Berkeley and is very interested in these things right now. I was at LDL. It was just grilling me the other day. So thinking in terms of the greater community of people.
That's great. It's really good. Yeah. This was like both really exciting to see and also a little disappointing. I've been telling people I was going to do this, and I didn't deliver. But
I'm telling you, I've got so many.
Okay, so this is the momentum computing thing, and so instead of talking about momentum ratio, I'm talking about some other thing we're working on, which is building a NAND, right? So using a slightly more complicated version of that circuit, basically, we'll get to that in a second. What's a NAND gate? A NAND gate is kind of like the workhorse of modern computing, and it can build any kind of logic based off of it. And the idea is that it's basically a triple erasure, I'm gonna call it. Okay, there's some others, there's a negation also in here, and there's some flexibility actually. It's a two input, one output gate, but I've chosen here to just have the output be both ones or both zeros. But the truth is, what we found is a NAND is overly complicated. You can have like a sub NAND, which we're calling the control erase. So the idea is 4 bits, you instantiate into 4 wells like this. If you can erase one thing while preserving everything else, then you can NAND, right? You can just do that a bunch of times and you get a NAND. And so here's basically a particular control erase, which we're notating this way, which looks a little confusing, but it's actually intuitive. But,
Take my word for
I
it.
swear. So we're controlling on not x, which means we're erasing over here when x is 0. And we're erasing to the 1 state, which means we erase out. So that's all it means. And so this can be represented like by this arrow. We're just taking this bit and moving it up here, preserving everything else. And this is maybe what the input-output table would look like. And if you take 2 of these guys I was talking about before, you couple them, you throw some linear algebra on it, what you get is, now again, I'm not showing you the full thing because every time I do this, the phase space is getting higher, and it's tribute to control. But on the kind of information storage space, you see that you gain the ability to control so that you can create this kind of flow of information just in one place while preserving everything else. So this is about to end the first part of my talk, and I think I probably have 10 minutes or something left for the second half, so I'll go quick. But basically, this is where I'm just saying we're really kind of pushing pushing forward in all these energy efficient computations. And one of the things, of course, we're trying to optimize the NAND gate based off of what I was just talking about, and that's actually a really interesting optimization problem. We'll talk about that in a bit. We're kind of using machine learning and neural networks in order to observe non-Markovian trajectories, basically under Langevin systems, and pull anything we want out of it. Forces, in this case, this is a force. It's kind of unsupervised learning where it learns the force, but it can also learn stochastic entropy production and all kinds of stuff about distribution. So that's cool. And then at the bottom, we're working on building SPICE models, which is essentially what electrical engineers use before they go to the layout of actually making a circuit as a way to kind of interface. And this I'm really actually happy with because here's a bit flip. Here's a little picosecond bit flip here, where you can see there's a stochastic start state because there's noise in the system. It starts at one of these 2. Then we do this little spike intervention. This is a current with an actual magnitude. These are parameters taken from literature, things people have built, and we do this little spike and we swap these bits. And of course, Gavin did bring up yesterday, like how much do we trust SPICE? And that's actually part of what I think what's so important about this work, is we designed through phase space and potential energies and stochastic thermal these processes. Now we're simulating them in SPICE, looks like they're viable. The question is, does that then correspond to experiment, and how does our estimation of dissipation track through these 3 levels? So this is going to be really interesting. And the last thing, there's an erasure, and this is part of that control erasure that I was talking about. So we're putting this all into SPICE.
So why don't you take like 15 minutes for part 2, if that works for you?
That's great, yeah. Okay. I thought I was going to be, I was like, I have this down, it's going to be 50 minutes, so fast. Okay, so part 2. So here's where the speculations begin, right? I was given permission. I try to avoid. I'm always like, I need a physical system. It needs to be simulated. I need to have measured something, or else I'm not going to talk about it. But you guys gave me leeway. You said,
Let's
talk about
go
stuff you don't understand.
Yeah.
So here we go. AI works now. I think whatever works means. I think we're gonna have to agree with this one. And I didn't ever think I would be saying this. I'm a bit of a skeptic, but whatever it's doing is very impressive, and it's certainly convinced a lot of people that it's working. Enough that I have to say, like, it's very effective at whatever it's doing. And there is a problem though.
It's very effective at convincing people.
It's very effective, which maybe that's intelligence. Who knows?
Yeah, right.
It's definitely not profitable though, right? It's profitable in the way that you can, because people are convinced, you can get people to feed you money to work on it, and you can say, I'm going to be the most expensive company of all time, even though I've never generated profit, and people are like, yeah, that makes sense, right? And this is part of our economic system. It's based off speculation, and people get phenomenally rich on speculation, and we can argue if that's good or bad, but I'll avoid
Is
that.
that actually true though? Like it helps people code and there's like stuff like AlphaFold and things like that. Like that's actually
Those business licenses haven't, at least they've not reported revenue from sale of business licenses, that kind of stuff.
Oh, you mean is it true if they're making money or not?
Yeah, like they're
I have not.
making something.
The people who work for the company are making money,
Right.
for sure. The company itself, I don't think any of them.
It has large revenue, but also just large.
But
large
massive
Yeah,
cost.
huge cost.
Yes.
Just want to keep raising money.
Existential cost.
So we'll go to the New York Times and we'll trust that they know what they're talking about, even though again,
Oh my
this
God.
is debatable.
I'm sorry.
Yeah, right. This is the speculation part. So this is what they're telling people is they expect to lose $5 billion, right? So this is their positive spin on it this year. And this also, I noticed, does not include paying equity-based compensation to employees, which I think we all know is significant, right?
Yeah.
And also several large expenses. So if you ignore those things, they're expecting to lose $5 billion.
I would love to see,
There's so much you put into several logics.
I would love to see the Excel spreadsheet.
Yeah, well,
I'm sure a lot of people would, yeah.
okay, so this is increasing the credibility of the New York Times now.
Well,
I'm feeling good about the New York Times.
So,
the way it's reported.
what can I say? I think I tried to look up the numbers, and of course they're cagey, but it's something like $3-ish billion in training, and like 3 to 4 in like server costs, and then 1 to 1.5 in labor, or something like that. Right?
Yeah, but it looks like they're making 10 million people paying $20 a month.
Yeah. So
is
that's
quite a
something.
bit.
That's something, right? So, but we can kind of figure it out that their plan here is to aggressively raise it to $44 over the next
A
5
month.
years.
So $2 billion a year.
So maybe they're pulling in a little more than twice as much in 5 years, right? Which could maybe just barely cover their costs now,
Now,
if they didn't get any bigger.
Right, but they're not expecting they're expecting the money to come from new science that their AI invents or something, right?
So that's what I'm
Something
saying is like,
crazy.
Is
this is-
science to pay for?
But yeah, what has science ever done?
Wow.
Well, they're like, oh, this our AI is gonna invent new drugs or like life extension or something, and we'll
Yeah,
sell that.
or
figure out fusion, life
It's gonna
extension.
cost us money, man.
Yeah, well, and this is
No,
fine,
you see, how much people pay for that?
right?
Well, yeah, how
That's
does
just-
AGI work? General intelligence would presumably would.
If it works,
If it works, it would be.
Yeah, worth trillions of dollars, or
Trillions of
it
dollars, so,
wouldn't
you know,
even have a
that's
number
the-
on it.
That's the VC thing, right?
Yeah.
So just to be fair, my claim is not that fantasy AI is not profitable.
My thought is that the VCs are paying for fantasy AI.
Yes.
Yeah,
That's
I think
exactly what's
I think
happening.
that's right.
Business pay for fantasy a lot of stuff.
Yeah, that's the speculative nature of our markets. Yeah.
Yeah.
Since I'm working in a fantasy company, yeah, that's how it works.
And I'm not trying to claim that it's good or bad. I'm just saying it's not profitable.
Yeah.
Right.
And this is actually not even a plan to be profitable. This is a plan to cover expenses if they stay the same, and they know they're not going to stay the same. Their actual plan to keep going is to get somebody to give them $5 trillion, right?
Yep.
So
Trillion, by the way. T.
yeah,
That was a
but,
T.
T.
Yeah. Seriously, seriously, I'm talking about raising trillion.
Yeah, right. And so they have these business solutions,
Right.
Yeah.
and I just want to point out there's a real difference, and this is kind of what you're saying, right? There's business solutions which try to predict the future and say energy is going to cost this much, so I need to raise my prices this much, and this I'm going to keep this market share, or I'm going to get this much market share from Anthropic for some bizarre reason. But of course they're kind of diversified, right? Like 80% of ChatGPT's income comes from individual people. But the scientific solutions, which is the ones we're all interested in, right, these are a lot safer if you can do them because you're actively changing the future. Right? So the idea is,
Safer.
I think so. I think so because for the person, for the investor.
Oh,
Oh.
Yeah.
This is a risk management talk.
This is it's an AI safety talk where we hear about the safety of the AI companies. Yeah, the safety of the AI investors.
They need to stay around in order to keep doing research potentially. So one of the cool things here is like the scientific solutions are straightforward even if they're difficult, right? So the issue here is that they're too resource intensive, and by resource I mean energy, because for me the story of everything is energy.
Well, the other resource is just silicon. I mean, we're maxing out how much GPUs TSMC can do.
I didn't even think about that. Yeah, it is. So it's like at some point the LLM training is taking away from other stuff that might be more useful. So there's a supply side answer, right? Make more energy. There's a demand side answer, which is you got to make the large language models cost less energy, or somehow you do the same thing or more things with less large language models. It's really straightforward. And people are working on the supply side. There's no question, right? Nuclear reactors, specific fusion just got like $1 billion. And I don't know, maybe these are good things. Like if we get fusion, it's amazing, but it's a bit of a tough sell. But I want it to work. But
It's fantasy energy.
it's fantasy energy.
Exactly.
But I'd rather have fantasy energy than fantasy AI because I feel like that's the actual requirement. And kind of like what Gavin was saying, there's a heat issue of pumping up energy production. At some point, you're making so much heat that you're causing a new crisis. And so energy demand is just as important and just as, it's not really, I was thinking earlier this week, I thought maybe it was negotiable. Maybe we could make the supply so high we wouldn't need to deal with demand and I'm wasting my life. But now I'm thinking, no, this is actually really important. And so you got to ask, like, can we look at biology and say there's evidence that we can compete with less energy? My intuitive answer is yes. But I also realized that the CPU on my new computer, the M3, it uses like 30 watts or something, 20 to 30 watts. Estimates of the brain, it's something like that, right? Like 20 watts or something. I
forget.
Yeah.
I'm 10-ish watt, yeah.
So
It's about, I think it's 10% of your overall budget, so energy budget goes to your brain, I think.
So it's just, I'm not sure. I'm not sure if biology is the right way to go, just because of that. Because I also know
It's not good enough?
Well, 30 watts to 20 watts?
Yeah, but if my brain's better than your laptop.
Well,
depends on-
That's arguable.
How fast are you at multiplying matrices?
So this is the problem. Like a computer can multiply with matrices way better than I can.
Yeah.
Right?
Right.
So it's really hard to make apples to apples comparisons. In fact, I was gonna put that on the slide, and I'm not even kidding. The estimates of how much energy the brain costs, they vary by 10 orders of magnitude. Like, literally 10 orders of magnitude.
Different
So,
people.
different people.
Have different burn rates, maybe. I don't know.
Wait, 10 orders? How's that
No names.
possible?
I don't know. It's because I mean, you guys know we don't know how the brain works exactly. It's really hard to
It's
make
true,
that
but
apples to apples.
calorimetry is easier than
The problem
consciousness, you know,
is
so-
not the energy, the consumption. The problem is measuring how much compute your brain is doing.
Oh, I
on a
see.
weighted
Yeah,
comparison.
yeah.
And that does vary. I mean, I'm sure that varies from person to person.
So I don't know. I don't know if we can look to biology. I want to, but I just want to point that out that I was actually surprised by how efficient computers seem to be right now. Now that doesn't mean that there's not obviously a bunch of room according to the laws of physics. So is momentum computing a good answer to this, right? I obviously want to say yes. And it's possible, you know, and it would take clever engineering and a lot of capital to start building something with new architecture, and it may eventually be necessary. But along the lines of what Gavin's saying, is that maybe you just can't compete with transistors forever. We're going to need to change because of the amount of heat that we're creating. So if we want to do a certain amount of compute, it in fact fundamentally needs to be cheaper. So maybe the will is there to actually do this. But I will say there are some signs that it's going to be harder and harder to do this kind of momentum extraction the more complicated circuits get. So this is for the control eraser. Here's a simulation, and something that you can see is that now we're kind of flipping one thing while storing other things, and we've had to add another dimension that I'm not even showing for control, right? And so you can see there's obviously a problem. There's this like bifurcation where these fixed points annihilate, and then these things just bounce down, bring down a bunch of energy. We thought, okay, we'll save that. We're momentum computers, right? We'll fix this. It's proven to be very difficult. And in fact, like here's one thing you think, okay, well let's start absorbing some of the energy by kicking it back up, but then that causes fidelity loss, right? We're starting to see this trade-off. Okay, we want to reduce the energy, fidelity pops up, right? Which is something we thought we kind of circumvented. So there's, as the systems get more complicated, it may be that this disappears. But you know, we're still working on it, and we're going to see. There's no reason to just throw that out because it's hard all of a sudden, right? But there are kind of energy demand solutions that we can do now, based off the hardware that we have now, and these might feel actually quite familiar to what Gavin was saying the other day, which is like, we know that we pay an energy for fast computation. We know we pay an energy for accurate computation. So what if we slow down, and what if we're less accurate? And theoretically, that should give us some kind of advantage. And if we can find smart ways to do that, it might not cost us much success. So briefly, I'm probably right out of time.
Yeah, I mean, does 5 minutes? Or
Yeah,
so.
5 minutes is great.
Yeah.
So basically the idea is let's double down on hardware that's like low power, stuff that trades speed for efficiency. I don't know how much we need fast inference, fast training. It's like, if we look at this plot, take it seriously, you know, if we take 10% more time, we could actually have a lot of energy savings. And maybe that's okay to wait an extra 10 days or something for this result, that we're gonna then use that model for so many things. When do we really need fast inference, right? If I'm talking to ChatGPT, it will make me a book, and it will take me 15 minutes to get through all the stuff that it answers. Why is it answering so much? It could have done, it's providing a lot of text very quickly that I don't necessarily need. So maybe it can be tuned to the fact that I'm having a conversation and just make a small amount of inference. And maybe I don't even use all that sometimes. I think that's too long, I'm not gonna read it, right?
But is that easier to do or harder to do? It's
I
gonna
actually
cost
don't know.
more, right? I mean, writing a shorter letter, according to Samuel Clemens and other people, right? It's tougher. I didn't have time to write you a short note, so I wrote you a long, you know. I just wonder if it's easier or harder.
My
Just
intuition-
a lot less energy.
Sorry?
Just spend a lot less energy when you do. Like a shredder.
But you have to start with a long letter, use it. I do. Start with a long letter before I make a short one.
And
I'm
this-
just- anyway,
well,
I'm sorry,
This
that's-
is actually how O1 works. Like the newest ChatGPT, it does a bunch of thinking beforehand
Sure.
and then summarizes it all, and gives you something shorter. So it's exactly like this.
I would think so.
Yeah.
Just because that's how humans do.
This is the chain of thought.
I guess what I'm
Yeah.
saying is not to create a shorter prompt that encompasses everything, but just to only give you a couple sentences at a time, and then you can prompt it for the next 2 sentences, prompt it for the next 2 sentences, and then it doesn't need to be so fast. That's more what I was thinking. And yeah, I'm going to go back to biology. Like, we know biology can function very intelligently on lower timescales. There's some thoughts here that slowing things down. Maybe we don't need to be this fast all the time. Similarly, maybe we don't need to be this accurate all the time, right? We have these very fancy deterministic computers. We spend a bunch of money, time and energy making them deterministic. But then we run stochastic gradient descent when we're training a large language model. It seems so silly, right? It's like
we're 1 byte, 8-bit floating point.
and then you at the end you toss it all out and you quantize. And it's like it feels like there's just there's got to be some way to bring stochasticity into the hardware, into the algorithms, right? Like I think a big reason ChatGPT is so good is not just because of the data and because of the transformer, but because of how good autograph is now. It's like way better than it used to be, you know? Like it's crazy how quickly you can do automatic differentiation. I don't know what that algorithm is, but it's like from 2011 or something. Like, people didn't have it before. It was tricky to calculate loss functions and gradient. I don't know. It's easy now. I don't have to think about it. So it's just calculus. Yeah, but but shouldn't we just approximate it? You know, like it's a bunch of products. Right? It's a product rule or chain rule. So yeah, there's this paper which I thought was kind of interesting out of Chicago, Cal Floyd, and basically the idea is they're trying to learn some non-equilibrium thing. The thing I want to point out is what they're showing is, of course, and this is not surprising, that you really don't need a lot. Like how well do you need to get close to the actual gradient? And they determine it's almost, as long as it has any positive overlap, that it's pretty good, that you can do a good job. So it's like, you can have really inexact gradients and still learn a lot. And so I'm wondering how much can we just, maybe just even software, run a stochastic algorithm? Yeah.
Oh, I was just going to say that Michael Hinch.
So anyway,
Yeah, from Hinch. He was doing sort of a stochastic gradient descent, including momentum, as like an additional degree of freedom, and actually found that at times not following gradient straight down, but sort of having this
Sure.
momentum taking you between wells. Was,
People,
Yeah,
people do that.
That's pretty,
standard.
Yeah.
that's very standard.
Yeah, and there's a win. There's a lot of good.
But it's still deterministic.
right.
Yeah.
Yeah.
There's like, as opposed to,
If you
People,
add
people,
points-
so people don't actually use stochastic gradient descent nowadays. They use momentum-based gradient descent.
but it,
Okay.
Yes,
all the
but
same.
that's all the same.
it's all the same. Yeah.
what
Yeah,
do you
but
mean
that's
it's
been a
all
long
the
time
same?
ago.
It's just
Yeah,
like
yeah.
you're still doing the same. It's still the same fundamental argument, like where you're like,
It's
I'm trying to
still
get this
step by
gradient. I
step.
take a small sample. I calculate the derivative over this small
Yeah.
sample, and then I move based off of where I'm.
But
at.
you also just track
And
your,
you track a little bit of
second
memory.
order or
Yeah.
like momentum.
But it's still very
you
much
get
a
out of
deterministic
wells.
algorithm. And so
And
I'm
it's like the standard
curious.
optimizer.
Yeah, the standard optimizer, like Atom, if you've heard of it.
Right.
Okay, so anyways, yeah, stochastic algorithms and also hardware. I think right. Like, what if we just start letting our hardware mess up, and it all of a sudden is way cheaper, and that things just work? I don't know. I'm noticing that, but I've been asking these people who are training, and they're like, I'm like, what if you do this? It's like, it kind of still works. What if you take this out? It kind of still works. You could have the brain out.
Yeah, robust. Yeah.
So lots of wild speculation. This is where this is supposed to start, but I think since I'm out of time, I'm just going to say I really don't think that AI currently delivers $40 a month of value to enough people. So I don't think that plan of charging more that's only going to cover the cost now is good enough. So I'm just going to throw that out there. I also am going to say intelligence is here, largely in not. And then I was going to tell a little story about introduction to ChatGPT.
Let's do it. Or,
Okay, so just really briefly, this is my experience of coding with ChatGPT, which is that I ask it something like, I want to write some Python code that can open a saved NumPy object, append to it, close it again. Help me with that, right? I'm just going to ask it that. And it says, like, yeah, sure, let's use save and numpy load to do that. And I'm like, okay, that will work, but I already know how to do that, but okay. Can you do that with the context manager, right? So that I don't like leave stuff open, and can you also do write only, because I'm trying to save memory, and this thing could be really big, and I'm just trying to add stuff to it. And then it's like, okay, yeah, let's use the numpy memory map, because that's for memory efficiency. Of course, I run that code, I get an error, I tell it about the error, it's like, oh, I see that error. And then I'm like, okay, well, there's no error now, but now it's just loading the whole thing every time, then it fixes it, but then there's an error, and I just end up in this like little loop of trying to fix things and then not doing what I want back and forth, and then I get frustrated at a stack exchange, and I fix it because HDF5 is the actual way to do this, because that's not what numpy arrays are for. And the thing is, it got me thinking, like, is it because it doesn't know the difference between good and bad ideas? It's just trying to do what I ask it. This was my theory. It's just trying to do what I ask it, interpret it literally, and I said I wanted to open an numpy array and append to it and then close it, right? It wasn't thinking, what did I mean? What I actually meant was, and then take my two questions together and think, oh, I want a memory efficient way to do this, so actually it doesn't make sense to do it this way. So instead, this was a couple weeks later, I opened up the same notebook and I was like, can we continue that conversation we're having? Because of course I talked to like you for some reason. And it said, great, let me summarize all this useless stuff that I already told you, which it did, at a waste of energy. And then I said, I'd like to know if you think this is a good way of handling the data or not. And it did know, right? It gave me, again, way too much text, but in that text was, MemMap does not have native support for appending a data class, right? Like, this is not what it's meant for. And we're doing this weird workaround, it doesn't really make sense. And maybe you should use HDF5. And then I said, okay, let's go, let's HDF5. And it was like, sure, and it told me everything that I already knew from Stack Exchange. But this was making me realize that it does seem to know the difference between good and bad, it's just not self-reflecting.
Well,
So
partly could also be because like the models are trained to be like helpful assistants, but also like follow user instructions, right? So like it doesn't want to like contradict you if you it's like part of the training.
Yeah, so these were my two
Yeah.
wild speculation
Yeah,
ideas from
yeah.
this experience is I want to do anti-training. Give it impossible tasks and make sure that it's bad at the impossible tasks.
I just like to say it doesn't know what it doesn't know.
Tell it doesn't know. It should know if something's impossible. It should know if something's a bad idea. If something's a coin flip, it should give you a coin flip. If something's 70-30, they should give you 70-30. It shouldn't pretend that it knows stuff it doesn't. And we learn that through human experience through hard lessons, right? So maybe we need to do some fine tuning that gives ChatGPT some hard lessons. And the other thing is active refinement. What if just it always is asking itself, is this a good idea? Now it turns out that I'm just behind the times because they're already doing both of these things, right? I learned that this week. So So I'm behind the times, and I don't know if this is depressing or not, because I thought, of course, this would solve the problem. And I just want to close by saying I keep thinking that. I keep thinking that the solution is easy. I'm like, you can see what it does, just loop it into itself, have it talk to itself, have two of them, and then this one can program, and then it talks to this one. And I know everybody else is thinking the same thing. It's not like it's a big mental leap. And I know that some very smart people are getting paid a lot of money to do this, but 2 years later, it's not fixed. So it has to be harder than it seems. And so I'm just not so sure we're as close as it feels when you're using them. On the other hand, I'm not at the forefront. I'm more like your average user of ChatGPT, which I still think is an important demographic, but like the people who are really into AI, like I talked to Adam, and Adam's like, it's a better coder than me, and I was like, that's crazy, because I know you're a good coder, and I'm not a great coder, and it's worse than me. But then, in fact, it's because you're using a totally different tool than I am. And that tool was trained on different data and fine-tuned differently or something. And I think you're using the same thing. This is called Cursor. And apparently that thing is amazing, and I just haven't used it. So,
I think it's also partly you've got to know enough about the domain to ask the right questions and to spot when it's talking rubbish.
I think that's true, and I think you also you become better at prompting it.
Yes,
getting
of course.
the thing. That's a huge part of it.
Just
So when you were going through your thing, I was like, oh yeah, that's not how you guys.
right,
But
so you,
that's just like not the right way to use that tool.
but can't it just do that itself? Shouldn't it, if it's intelligent?
So people talk about whether or not like this whole prompt engineering thing is going to become passe very quickly because of exactly this.
Oh.
But
Well, why would it be passe? It would be more useful, wouldn't it? Or, what do you mean?
Well, eventually it might just know what you it might just know what you're trying to get at. You don't need to
What
like
do you mean you
fancy.
could get it so good that you don't need to be an expert user to get it to
Exactly.
what you want?
That's the idea. At least I'm not sure.
And yet,
If it would at least come back with a list of what you might mean, it could say, well, there's several things you might mean, or do you want to do this? Do you want to assume this or that, or whatever?
Yeah.
I'm sorry, Kevin.
Oh no, just the sense I think you mentioned that ChatGPT comes to the scene for whatever it was, and it was amazing, this huge leap. And then you get this, and then we all see the problems of it. And they've been often working on this, and it doesn't seem to have got really fixed these problems. These problems could be fundamental, maybe just to the fact that you're just training the thing to do next token prediction. That's underlying it somewhere, and you feed it a lot of crap when you do that.
But to what extent?
Yeah, I agree. Yeah, I don't think it's
But to what extent? I mean, everyone here knows better than I. I mean, I read in the paper how expensive it is to train these models. I mean, what is the iteration time for like I see what the problem is. I need to change the way Is that a little tweak, or does that require 150 billion?
Well,
a
lot of times,
stages, right?
yeah,
So-
they train small models to like try things out, and they try to only do these big training jobs when they like are confident it's going
Once
to
they
work.
got the solution.
Once
Right.
but sometimes it doesn't work. Like there was rumors that GPT-4 or GPT-5 it did the whole training job and they just like threw it away because it didn't work.
And that's why we haven't seen it.
That's why we haven't seen GPT-5. That's the speculation.
But this also happened with GPT-4.
Also in GPT-4, yeah, interesting.
It was
Yeah,
trained
Because it was worse or it didn't?
yeah, it was worse.
So
Or
they had to redo the.
yeah, because it's just like so like there's these nice scaling laws, but like there's weird things that happen when you're training like on like tens of trillions, hundreds of trillions of tokens. Like
Sure.
might not weird things happen, and you're like, oh, we screwed up.
Well, certainly, if I write any code where this is me, but I mean, I would never in a million years be able to write the code that's going to work after I run it the one time that costs me, king's ransom, and then at the end, it's always going to be.
Yeah.
There's going to be something unforeseen, right?
Right.
Surprising it's worked at all, really.
I'm thinking about the speculation you had about whether or not next token prediction is enough, and just like everyone or a lot of people in this room have a very deep understanding of exactly the kind of computational structure of what it means to predict next symbols based on histories, and I'm wondering if that understanding can help us understand the limitations of kind of the types of behaviors that just predicting the next token optimally has, and what else would be needed.
We've done some work looking for the epsilon machines. You can trade off basically the prediction horizon and the history horizon together. In a lot of cases where you can all you need to do is predict the next symbol that had a long history, but it can go other ways, like other classes of problems. So that's an interesting direction we can push in to understand what the trade-offs are between those different horizons.
So wild speculations ends here.
I don't know.
For-
I think we're still going. It's unclear.
Yeah,
Like that begins here, right?
it begins.
Yeah,
Yeah.
it is.
Yeah.
Good question.
Let's,
It's there. Yeah. No, I don't know, and it's a really good point. I think that a lot of people in this room have a really good idea about prediction, really strong, sort of mathematically and analytically. And I'm curious to see, like, especially the stuff that Alex is doing right now, starting to use this on these totally different kinds of systems, right? And like discrete and continuous data, categorical data, strings, right? But see where that goes, because this could be incredibly informative.
Yeah, yeah.
Well, thank you for the talk.
Yeah.